Hey, what's up, guys? This is Chung here, and today we're gonna talk about a graph problem here, number 1136, parallel courses. Yeah, so let's take a look. You're given a relations x and y, where x is a prerequisite course and y is the course itself, which means if you want to take course y, you have to take x first, and then you can take y. And So basically, you're given a list of these relations from one course to another, and you need to return the minimum number of of the semesters needed to study all courses. So on one semesters, you can take as many courses as you want, as long as that course can be taken right now, right? For example, this one here. Uh, in order to take course 3, you need to take 1 and 2, right? So basically, both 1 and 2 after you have to take 1 and 2 first, and then 3, right? But so in one semesters, you can take as many courses as possible, right? As you want. So as semesters 1, you can take 1, 2 because both 1 and 2 doesn't have don't have any prerequisite courses, right? So the first semester is 1 and 2, and the second semester is 3, right? And here, and if there's no way, what? Okay, okay, yeah. Sorry about that. Some hiccups about my pen here. And if there's no way you can take all the courses, return -1. So what does that mean, right? It means, let's say, for example, this example 2 here. Uh, Basically, right, as you can see here, it's obvious in this case, there's no way you can take all the courses because all each course will depend on another course, right? So there's no starting point, right? So what does it mean? It means as long as if there's a graph, I'm sorry, if as long as if there's a cycle in this graph, then it means there's no way you can take all the courses. So okay, so basically, how are we going to solve this, right? So first, obvious, you need to construct a directed graph here, right? Since this is a directed, it's a from x to y, right? Since from x to y, it's a directed graph. So first, you need to build a graph with x to y as the edges, right? And then how do we traverse, right? And then we need another dictionary to store all the integrate of each node. Excuse me. So basically, if there's no integrate of a node, then we know we can take that node, we can take that course, right? And every time when we take a node, right, when we take a course of the node, we're gonna remove basically that edge or from this graph. So after we keep take after taking course 2, we also remove this edge from the course. So what does it mean? It means that every time when we remove an edge from x to y, the integrate of y will be decreased by 1, right? So at the beginning here, so the integrate of this is 0, 0, and integrate of 3 is 2, right? So once we take 1 as a take once we take course 1, we remove this edge, and which means this just 2 will become the integrate of 3 will become 1, and then we just keep keep removing the zero integrate nodes, right? So this is done, this is removed, and then this like node, the integrate of 3 will become 0, and then we can see it's now it's safe to remove this to take course 3, and it asks you the minimum number of semesters, right? So when you every time when you see a minimum numbers, then we know it's time to use the breadth first search, right? So breadth first search is usually used to find the minimum path, right? Basically, you need to use the breadth first search to this graph to see how many levels you need to take to basically to traverse all the nodes in this graph. Okay, I think that's pretty much about this problem. Let's try to code here. So like I said, we need a graph here, right? And we're gonna initiate with like a default dictionary with list because one node could have multiple neighbors, right? And then we also need an integrate dictionary here to store the integrate of each node. We're gonna like code with a, by default it's 0, right? So we just need to loop through the relations array to build the graph and the integrate first. Relations, right? And uh, prerequisite, right? Prerequisite is the relation uh, 0, and the course is like relation 1, right? And uh, graph dot, since we're building a directed graph here, right? Prerequisite dot append, right? So we're gonna append this course to the prerequisite dictionary, right? And then what? And then that's for the graph, and for the integrate, right? In integrate for the course course plus 1, right? That's how we build those two dictionaries. And then what? And then we need to start. We need to have a starting point, right? How do we start, right? So at this moment, after building this one, our first iteration will be all the nodes that doesn't have will basically doesn't have any integrate, right? So we're gonna have a queue here for the breadth first search here, DQ, and so how do we get the nodes without any don't have any integrate, right? So as long as the node is, we have n here, right? So we know there's like node from one to n, right? As long as the node is not in the integrate dictionary, then we know it doesn't have any integrate because at this moment integrate nodes dictionary only stores the nodes who have the integrate, right? So I for I in range, right? Starting from one to n, right? N plus one basically, right? Uh, if if I not in integrate, right? That's our starting point, right? So we just do a while queue, right? Do a while queue, and then our answer, right? Our answer will be the level of the traverse, right? So every time we do a traverse, we just add the answer by 1, and so below is going to be the regular uh, level breadth first traverse. Gonna do a length in range, right? Length q, right? have a node, right? I'm just gonna use the node or the vertex. I would say the vertex. Uh, Pop left, right? And then for all the neighbors, right? For all the neighbors in the vertex, neighbors, we're gonna have get the neighbors from this graph, right? What do we do here? We already see this for vertex, and then we're gonna need to remove decrease the integrate of the neighbor by one, right? And then if, right, after decreasing the integrate, we need to check, right? If integrate is equal to zero, right? If it's zero, then we know it's ready to be to this course is ready to be taken in the next level uh breadth first traverse, right? So we just add this one q append, right? Append to this neighbor, right? And in the end, we just return the answer. Yeah, that's basically the main structure here. But we don't forget, we also need to check if there's a way of taking all the courses, right? Because let's say if there's not enough, if we didn't take all the courses, right? How do we check that? So we can have like simply have a courses took like variables here to zero. Basically, every time uh, we uh, we pop, right? We pop this a course, which means we took that course, right? And we just increase this course took by one. And in the end, we can simply check if we have taken all the courses, right? Comparing with the end here. So basically, if it returns answer, if if the number, if the courses took is equal to n, right? If they're the same, because we know there are n courses. If they are the same, then we know the answer is the one we need. Otherwise, else just minus one, right? Yeah, I think that's pretty much it is. Uh, let's see. Hmm. Uh, yeah, sorry. So this here, it's yeah, neighbor. Yeah, forgot to add the neighbors here. Yeah, cool. I think that's yeah, that's pretty much it is. So basically, we just built like uh the graph and the integrate first, and then we initialize our starting point, which are the nodes are the vertices, right? That don't have zero integrate, and then we just keep doing it. We do a breadth first search, and we just keep every time we process see a vertex, we remove the edge. Basically, we reduce the integrate for the neighbor vertex, and if it's becomes zero, we add it to the queue, right? And then every time, every level, we increase the answer. And in the end, we check if we have taken all the courses, right? If there's a cycle, and since we're removing all the nodes here, right? and we cannot took out the course. And give you an example here. So let's say we have a 1, 2, and 3 here, right? Let's see. There's a cycle, and then there's like 4 here, right? So follow our code here. The first element in the queue will be 4 because 4 is 0, right? So when we have 4 here, we come here, answer +1, and then we see all the ranges, all the neighbors are 4, right? So we see 2 here. So what's the integer for 2 at this moment? So it's going to be 2, right? And after we process area removing 4 from the graph, this this integer will become 1, right? So but 1 is not 0, so there won't be any new element appended to the queue here, right? So once this is done, the queue will become empty, and then we're here, right? So in this case, the course took is only 1, but instead we have 4 here, right? So that's why we can use that. That's why this thing will stop if there's a if if there's a like cycle, because we once you the moment you reach a cycle, basically the while loop will be stopped, because there's no way we can get like a zero integer in first cycle. Yeah, okay, cool. I think that's pretty much it is. All right, thank you so much for watching the video, guys. And okay, I'll be seeing you guys soon. Bye.